Let's start today's seminar, and we are happy to have Hugtenburg from the University of Edinburgh. The title is on the screen, Open Gromov-Witten Invariants from the Fukaya categories. Please, Kai.
Hi, thank you all for coming, and thanks very much to the organizers for inviting me. Yes, so as said, I will talk about how to obtain open Gromov-Witten invariants from the Fukaya category. I don't claim to have a full solution, but there are some things that were done in the past and some bits I add to the story. Please just interrupt me as much as you can if there is anything unclear, or just raise your hands or just unmute and ask your question or type it in the chat. That will make the talk a lot better. Okay, so yes, and there we go. So the story, as always, probably in these seminars, will start with mirror symmetry, and the first incarnation of mirror symmetry is an enumerative symmetry, which was first discovered by Candelas, De La Osa, Green, and Parks in 1991, and they found pairs of spaces X and Y, such that if you consider X as a symplectic manifold and Y as a complex manifold, then the enumerative invariants of X and Y are going to correspond to each other. And the enumerative invariants of a symplectic space, then we're talking about the Gromov-Witten invariants. And for the complex space Y, we talk about the period integrals of the space or family Y. And you can make sense of this at genus 0, so considering genus 0 Gromov-Witten invariants, but you could equally, like work in progress that's happening, make sense of this at higher genus. But this talk is mostly focused on genus 0. And so as I said, like the first incarnation was enumerative mirror symmetry, and later in 1993, Morrison reformulated this sort of enumerative mirror symmetry in terms of variations of Hodge structures. And I'll explain later what these are. And there's like just an isomorph, like what then is happening is that associated to X, there is a variation of Hodge structures, and that is isomorphic to the VHS associated to Y. But just the data of the VHS might not be enough to recover enumerative invariance. You need an extra piece of data, which is a splitting of the Hodge filtration. But once you have that, you obtain enumerative invariance, and then those for X and Y are going to correspond to each other. And this was all about the Calabi-Yau setting, where you can talk about variations of Hodge structures. And then later in 2001, Baranikov made a similar statement for Fano mirror symmetry. And in this case, you shouldn't talk about the variation of Hodge structures, but the only thing you can obtain is a semi-infinite variations of Hodge structures. And that just has to do with the fact that you lose the fact that you have a Z grading. So now your VSHS is only Z mod 2 graded. Okay, so that is another version of mirror symmetry, sort of Hodge theoretic. And then around sort of 1994, I believe, Kontsevich conjectured and packaged this all into what's called a homological mirror symmetry. And he said that actually these spaces X and Y, there's a much deeper mirror symmetry, which is at the level of A infinity categories. That should be that associated to X, there's the Fukaya category, and associated to Y, the category of coherent sheaves. And these two categories are going to be quasi-equivalent. And moreover, if once you have established such a quasi-equivalence, this will imply that the enumerative invariants of X and Y are going to correspond to each other. Now, what is the idea of the proof that if you have homological mirror symmetry, you can obtain enumerative invariants? Let me give you the outline on the symplectic side, at least. Is the first thing to do is to associate to the Fukaya category, just any A infinity category, a variation of semi-infinite Hodge structures. Then the next step is to show that this variation of semi-infinite Hodge structures agrees with what's called the quantum variation of semi-infinite Hodge structures, which is the one that we'll know about Gromov-Witten invariance. And then the final step, as I said, you need some extra data on the VSHS, which is the splitting. And so you need to, in some way, characterize the correct splitting to obtain these enumerative invariants. And let me tell you what has been done about this in the past. This associating to an infinity category of VSHS. That was done by Getzler, and Katsarkov, Kontsevich, and Pantev, and Shkliarov. Then showing that if you do this for the Fukaya category, then it agrees with the quantum VSHS. This was announced in work by Ganatra, Perutz, and Sheridan, and I add a tiny bit to that.
Excuse me, you mean that in the part 1, you do not assume that you deal with Fukaya category? It's more general setting, yeah?
Yeah. This is much more general.
Yeah.
Can be done for any infinity category, like DG category, but yeah. And then the final bit of data is to consider the correct splitting. Now, in the Calabi-Yau setting, this has been done by Ganatra, Perutz, and Sheridan. But in the Fano setting, this is much more difficult. And Amorim and Tu do this for semi-simple quantum cohomology. They characterize what the correct splitting should be. And sort of, you have a statement that you can obtain enumerative invariance from the Fukaya category. Okay. Now, let me tell you what are these variations of semi-infinite Hodge structures. And in the rest of the talk, I'm sorry to give them a different name. I will call these formal TEP structures. This is terminology introduced by Hertling and Savenheck, and it will make talking about all the structures much easier for me because we'll need some extra piece of data. Okay, so what is this?
TEP for those who do not know? What's abbreviation for what?
Yes, I will tell you in a second.
Okay.
Thank you. Yes. So what is the algebraic setup? We just start. I mean, probably this is nice with the field of characteristic 0, and we just take any K algebra R, and I will often refer to these as the parameterizing bulk deformations. And then the main gadget of interest is what is this E, which is a free and finitely generated R join U module. And then what we're going to talk about is these TEP structures. And the T, or I think that stands for twister structure, is just a flat connection, which maps, like you have to do things a bit formally, and it maps derivations on R, tensor E, to U inverse of E. So what this is saying? This is saying that it's a connection on sort of P1 times E. It's like, I don't know, spec R times E times P1. And it has a pole of order 1 at U is equal to 0.
What about infinity? I'm confused. If it's P1, so then...
Yes, that's a very good point. Thank you. Yes, I shouldn't have said P1. I should have said a formal neighborhood of 0. Yeah, that's like, because we're considering formal structures, you only know about a formal neighborhood of 0 in this formal structure. Thank you.
Yeah, and U has degree 2 or what? Or it doesn't matter for you now?
Yeah, but I will not talk too much about gradings, but indeed, like the connections should have like should respect the gradings in a certain way. And then the next piece of data is the E structure. E, I think, stands for extension, because you extend the connection to also care about the U direction. And this connection now has a pole of order 2 at U is equal to 0. And I won't talk about this much, but that means that sort of the behavior of the connection is fundamentally different from just having a pole of order 1. It leads to a lot of interesting phenomena. But since we only consider the formal structure, this will not appear in this talk. And then finally, the P structure, or the pairing, is just a covariantly constant pairing on E. And it satisfies a certain non-degeneracy condition, being that if you take E modulo U, then the induced pairing on there should be non-degenerate. And finally, if you know already about what variation of semi-infinite Hodge structures are, then you might recognize that the VSHS is just the same as a formal TP structure. And a VHS is a Z-graded formal TP structure. And the reason why I started talking about these TEP structures is because in what I'm going to say later in the talk, the main new thing I do is considering these E structures with respect to the open-closed map, which we'll get to. But these E structures are important. Any questions about this?
So it's a pairing of roughly fibers of E over the same point, not over opposite points, like in this non-commutative Hodge structure business.
Yeah. It's fibers over the same point, but since we're working formally, there's only really one point.
Yeah.
So,
let me ask the abbreviation. So the P apparently means pairing, but what does the T and the E stand for in 1 and 2?
so the T stands for twister, and I am unfortunately not sure where this comes from.
Yeah, if you have CP1, really, maybe you should think of this CP1 as a twistor sphere in the end. So then there should be two conditions at 0 at infinity. Yeah, so something like that.
Mm-hmm. Yeah, and then the E structure stands for extending the connection, so that you don't just have a connection sort of that takes inputs in derivations on R, but it also takes a connection in the U direction. Which
okay, thank you.
Let me give you some examples. So the first example is the TEP structure associated to quantum cohomology. And also let me note one thing, I will always only talk about formal TEP structures, but I will drop the formal from now on because otherwise I'll say that word 50 times. Okay, so in this case, like for simplicity, I'll just work with the ground field being the complex numbers, and the bulk deformation, or the space of deformations R is going to be the Novikov field, which you can think of as formal Lorentz series, like formal real Lorentz series in a single parameter Q. And then the quantum TEP structure is given as an R adjoint U module by the cohomology of X with coefficients in R adjoint U. And you can then define the connection. Well, the connection in the direction of the Novikov parameter is just given by taking the derivative in the Novikov direction. And then you do the connection matrix, and that's given by quantum coproduct with the symplectic form. So omega is the symplectic form in our space. And similarly, you can define the U connection, which is like another formula. You just take the derivative in the U direction, and then you have a U to the -1 term, which is given by mu, and mu is some sort of is a grading operator on quantum cohomology, but shifted. So like on HP, it's just given by p/2, but you shift it down by -n/2, where n is the dimension of X. And then finally, as I said, this one has a pole of order 2 at U is equal to 0, and the polar bit is given by quantum coproduct by the first germ class of X. And let me remind you, how is this quantum coproduct defined? This is like as many constructions in symplectic topology is given by considering some moduli space of holomorphic curves. And in this case, you consider holomorphic maps from the 2-sphere into X. And for each degree beta in the second homology, you have such a space of maps. And this moduli space comes with evaluation maps. So we consider them with 3 marked points. And then we have evaluation maps, sort of evaluating at 0, 1, and infinity on the 2-sphere. And then they're just given by a push-pull formula. So given 2 differential forms, alpha-1 and alpha-2 on X, what we do is we first pull them back to the moduli space using evaluation at 0 and infinity. And then we push it forward using evaluation at the point 1. And this is then the... Yeah.
I mean, I forgot your assumptions on X, since you kind of speak in geometric setting, not infinity. Then X is what? Symplectic, Fano?
X is a symplectic manifold.
Oh, okay.
And I will brush a lot of technical details under the rug for now in this sort of like overview of what I mean. And then later I will state the assumptions on when you can actually make sense of the operations like this. Because unfortunately in symplectic topology, you always you can never do things easily, which is annoying.
You should spend 1 hour just for the introducing all the structures, and in the end, nothing depends on them. Yeah, okay.
Yeah, exactly. So I will just give you the simplest setup in which we deal with differential forms and push-pull formula, and hopefully this will make most sense to more algebraically minded people. And finally, so this is defined for us the T structure and the E structure, and then the pairing is just given by doing the Poincare pairing, and you extend that in the U direction. Let me give you an example of what this quantum car product is and what the connection looks like. So if we take our space X to just be the 2-sphere, then we consider a basis for that just by 1 and H, where H is the Poincare dual of the point class. Then the first germ class of S2 is just given by 2 times the point class. And we find that the quantum multiplication table is almost the same as just an ordinary cohomology, but now there is a new product, which is that H times H is equal to the Novikov parameter, representing the fact that if you take 2 points, there is a unique line or a unique sphere through those 2 points. And then you could write down in that basis, you could write down the connection. And as you can see, it's not a terrifying thing. It's given by some 2x2 matrices with some coefficients. So this allows you to do some very explicit computations with these connections, which is quite satisfying. And I recommend you do it at some point if you're interested in these things. Okay, so this was telling you about one of the TEP structures under consideration. And then the next one we need to consider is the TEP structure associated to an A-infinity category. And for simplicity, just for introducing the concepts, I will only talk about A-infinity algebras, which will make life a lot easier. So let's assume we have an A-infinity algebra over R. Just an R-linear A-infinity algebra. And then the first thing we need to consider are the Hochschild chains. And in a simplified setup, you can just represent Hochschild chains as a direct sum over all k of A tensor to the k. And then the A tensor to the k, you can actually quotient out by R times the unit, so the ideal spanned by the unit, to make the chain complex easier to understand. And I hope you have seen this before, but if you haven't, then what there exists on the Hochschild chains, there are going to be 2 differentials. There is a small b called the Hochschild differential, and there's a big B, or the cons B differential. And these anti-commute with each other. And just the Hochschild homology of your A-infinity algebra can be given by taking the homology of the Hochschild chains with respect to the Hochschild differential small b. And then the gadget that we're going to construct the TEP structure on is given by the negative cyclic homology. And that is, you take Hochschild chains, you now adjoin the formal parameter u, and then you take the total differential, small b plus u times big B. And you take the homology with respect to that, and that gives you negative cyclic homology. And one thing you might note is that if you set u is equal to 0 in here, then you obtain a map to the Hochschild homology of A. So in that sense, it's just, if you are familiar with Hochschild homology, it's just an extension of negative cyclic of Hochschild homology. So you take into account this cons B differential. And I won't precisely, One important thing to mention is that in order to make sense of TEP structures, remember that we need, one of the conditions that we needed is that the R adjoin U module is going to be free and finitely generated. But this is not obvious for an A-infinity category. But if C is smooth and compact, it's a long-standing conjecture by Kontsevich and Soibelman, that indeed the negative cyclic homology of such an A-infinity category is going to be free and finitely generated. And in the Z-graded case, this was proved by Kaledin in 2005, but in the Z-mod 2 graded setting, this is still an open conjecture. But in the rest of the talk, I will just assume that this has been proven. And then how do you associate such a step structure? I won't give you the formulae.
Briefly explain the free is in what sense?
Free that there is no U torsion. So it
was a module, right?
Yeah, exactly.
Okay. And finitely generated is also in terms of a module, or because there are also
just as a module over in this case R join U.
Okay, thank you.
I won't give any formulae for how precisely the step structure is defined, but I'll just tell you where to look for the definitions and the T structure. So this is the connection, sort of the R directions. That was first constructed by Getzler. That's also called the Getzler-Gauss-Manin connection. The E structure, this connection in the U direction, that was constructed by Shklyarov and by Katsarkov, Kontsevich, Pantev. And the P structure, which is also known as the higher residue pairing, this was constructed by Shklyarov and is an upgrade of the Mukai pairing on Hochschild homology, if you're familiar with that. And let me give an example of the sort of the main player in symplectic topology. The infinity category we consider is the Fukaya category of X. And the objects of the Fukaya category are going to be Lagrangians, and the morphism space from L1 to L2 is what is called the Fleur cochain complex, denoted by CF star of L1 and L2. And in the setup I'm going to talk about, I will consider a Fukaya category where there's just a single Lagrangian. And in even nicer, then we have a model for the Fleur cochain complex of just a single Lagrangian given by differential forms on L with coefficients in the Novikov ring. And then how are we going to define the A-infinity structure on this Fleur cochain complex? Well, again, this is going to be defined using moduli spaces of holomorphic maps. And the maps that we are now considering are this is the moduli space of disks which map to X and L. So that means that the disk maps inside X and the boundary of the disk, the S1, maps to the Lagrangian. And we consider these with both boundary marked points, so marked points on the S1 boundary, and L interior marked points inside the disk. So again, we will have evaluation maps on this moduli space. We have evaluation maps at the boundary, which map to the Lagrangian. And we have evaluation maps at the interior marked points, which map to X. And then how the A-infinity structure is defined using moduli spaces where we only have boundary marked points and no interior marked points. And how do we do that? Given a K tuple of differential forms on L, if we consider the moduli space with K plus 1 boundary marked points, we use the K of the boundary evaluation maps to pull back the differential forms to the moduli space, and then we push it back using the evaluation map at the 0th boundary marked point to obtain a differential form on L. And then again, we count all the contributions from different homology classes of disks, and we sum them all together by weighting them with Q to the symplectic area. And this will define for us an A-infinity structure on the category. And what is nice about this setup of Solomon-Tukaczynski is that we are not just going to consider a Fleur cochain complex, which is going to be linear over the Novikov field, but we can do something much better, which is where we consider our algebra R to be sort of formal functions on the homology of X. There's like in that sense, we can take take into account all bulk deformations that we would want to consider. So that's sort of by considering extra interior marked points, you consider a bigger family of A-infinity algebras. And what is the main gadget to compare the TEP structure of quantum cohomology to the TEP structure associated to the Fukaya category? This is the open closed map. And this was first already constructed in 2010 by Fukaya, Otto, and Ono. They construct an open closed map that maps the Hochschild homology of the Fukaya category to the quantum cohomology. And they show various results, like, for example, that it respects the module structure given by cupping by Hochschild cohomology and cupping by quantum cohomology. I won't talk about that. And how would you intuitively want to define this map is you now consider the moduli space with k plus 1 boundary marked points and a single interior marked point. And then remember that a Hochschild chain was given by a k plus 1 tuple of elements in the Fleur cochain complex. So that's k plus 1 differential forms. And then what you do is you pull back using the boundary evaluation maps, you pull back the differential forms to a differential form on this moduli space, and now you push it forward using the interior marked point. And that will give you a differential form on X. And then again, you take the sum over all contributions of homology classes of disks. And why have I put it as defined in apostrophes is because now actually in the geometric setup I work in, you cannot do this because this push forward along this interior marked point is not going to be well defined. So you need to modify the definition a bit. But for this talk, let's just assume this works. So this was the definition of an open closed map that just maps the Hochschild homology to the quantum cohomology. But that is not where the TEP structure lives. The TEP structure will live on negative cyclic homology and on the quantum TEP structure. And FL-Cubed and Ganatra in 2019 in a general setup constructs a negative cyclic open closed map, which will map the negative cyclic homology of the Fukaya category to the quantum cohomology I joined you. But they don't prove anything yet about the TEP structures. But the natural conjecture, of course, to make is that indeed this negative cyclic open closed map is a morphism of TEP structures, so that respects everything you wanted to respect. And this was announced in 2015 by Ganatra and Perutz and Sheridan that they have a proof of this fact. And what they consider, they will mainly work in the Calabi-Yau setting, in which case they only consider the T and the P structure, because in the Calabi-Yau setting, the E structure is not interesting. And moreover, they only consider this connection in the direction of the Novikov parameter. So they don't do full bulk deformations. But on the upside, they will consider a very general setting. And what is my result? My result is that I work under certain technical assumptions that were also used by Solomon Tukaczynski, which I will spell out in a minute. And I construct a cyclic open closed map. And now unfortunately, this will only apply to a single Lagrangian. So I don't get the negative cyclic homology of the full Fukaya category, but just the negative cyclic homology of the A-infinity algebra associated to a single Lagrangian. And that maps also to the quantum TEP structure. And this is then going to be a morphism of TE structures. Again, unfortunately, I don't have access to the pairing. And this will be covered by Ganatra, Perutz, Sheridan, so that together that will give a morphism of TEP structures. One advantage of my setup is that I can work with all bulk deformations, so that the T structure is respected sort of with all deformations. And one thing I should say about the proof is that my proof goes like in sort of the ideas are all the same for proving that the open closed map is a morphism of T structures. It's all the same as what Ganatra, Perutz, and Sheridan do, and they give good talks about this, so I won't won't say too much about it. The new bit is to also consider these E structures. And the extra ingredient you need there to upgrade a statement that the T structures are respected to the fact that the E structure is respected is to somehow show that the negative cyclic open-closed map respects gradings. Even though the negative cyclic homology is only ZMOL2 graded, you can still make sense of something that's called an Euler grading. And the statement that the E structures are respected is in some way saying that the Euler grading is respected by the open-closed map.
So you cannot extend your open-closed map to the, say, I don't know, inductive limits of over Lagrangians to construct some sort of a map which first does not depend heavily on the interaction. Because if you deal with one Lagrangian, which roughly speaking, this means that you deal with Fukaya category of Liouville neighborhood of that Lagrangian, yeah, and so then like some people suggest you should take first the inductive limit and then correct it by finding some Maurer-Cartan element which gives you the honest map.
Yeah. One thing is like I don't consider just a Liouville neighborhood of L. It's really L sitting inside X. So it does depend on the entire geometry of X.
It does or it does not?
It does.
It does. All right. So
Yeah,
you
yeah.
really need. I see.
Yeah, but so one thing you could do is if you take a generating collection of Lagrangians, you could consider the Lagrangian, which is given by sort of the union of all of those Lagrangians. And as a singular object, you should be able to deal with it in the same sort of way that I dealt with it.
Okay, but your map depends on some large pseudo-holomorphic disks, probably with a boundary on this. Okay, good.
Yeah. It's more sort of a technical, an unfortunate technical setup where you can only really consider one Lagrangian. But the idea should all extend very easily to the entire Fukaya category. So let me tell you about the assumptions I need, and these were made by this setup was considered by Solomon and Tukaczynski, and that's that I need my moduli spaces of disks with boundary on the Lagrangian to be smooth orbifolds with corners, and that is not a very strict setup. This is expected to hold in a very general setting. But the one that is restrictive is that I need my boundary evaluation maps to be a proper submersion. And in some way that's saying that there are enough holomorphic disks in our space. And what is the main example of this? Or like what's an easy example is, for example, complex projective space with the Lagrangian being the Clifford torus. Another one Lagrangian you could consider is RPN inside CPN. That also satisfies these assumptions. Or more generally, you can take flag varieties, and then the Lagrangian being the real locus. And what is the reason that I assume have these assumptions is because in this setup, Solomon Tukaczynski defined open Gromov-Witten invariants. And the reason why I started out on this project is because I wanted to obtain open Gromov-Witten invariants from the Fukaya category. So in order to do that, I wanted to compare them with a definition of open Gromov-Witten invariants that was already made, which was in this setup. And hopefully at the end of the talk, I'll have some time to say something about open Gromov-Witten invariants. Cool. The next part of the talk will be about applications of this. So if you have any questions about this, please ask now.
Sorry, I have a question from the last slide.
Yeah.
So is there a technical reason why your cyclic open-closed map does not immediately respect the pairing?
The technical reason is that in the analytic setup that Solomon Tukaczynski used, I can only produce an example where all my moduli spaces are smooth orbifold with corners and the evaluation maps are proper submersions if the holomorphic curves I consider only have one boundary component. So I could, and in order to prove that the pairings are respected, usually one considers this moduli space of holomorphic cylinders with boundary on the Lagrangian. And if I want to have any guaranteed examples where my assumptions are going to hold, then I can only work with holomorphic disk with one boundary component. And that's just some technicality that is unfortunate.
Thank you.
Any other questions? Okay, now I'll get to sort of the more interesting bit of the talk, which is applications of this of the conjecture that if we assume that the negative cyclic open closed map respects step structures, what information can we get from that? And the spoiler is it has to do with Gromov-Witten invariants. And in order to talk about those, I will first say something about the splittings, which was, remember, that's extra bit of data that you needed on a variation of semi-even thought structures to obtain enumerative invariants. So what are these splittings? Well, suppose that we're given just a P structure E, and then a splitting is just a linear map from E tilde to E, where remember that E tilde was just E modulo U. And what does it split? It splits the natural projection from E to E tilde. And since we have a P structure, we require that this splitting respects the pairing. So remember an induced pairing on E tilde, and we just say that this is respected under S with the pairing on E. What is the easiest example of such a splitting? If we take the quantum TEP structure, which was just given by quantum cohomology, join a formal variable U. Then we take the splitting, which just sends an element, a differential form in here, to the element differential form times U to the power 0. So sort of it sends alpha to alpha. And this is the splitting that will be relevant for Gromov-Witten theory. And I won't really spell out why, but the slogan is that if you have a variation of semi-even thought structures together with the splitting, then you can obtain a Frobenius manifold. And once you have a Frobenius manifold, you know how to obtain enumerative invariants. And this splitting precisely gives rise to the correct Frobenius manifold. Now suppose that we have two different splittings of a P structure, then you can just do a change of basis, which will be called the R-matrix, by writing one splitting in terms of the other. And this is just like follows formally that you can then write S1 of alpha in terms of a power series of S2 of some matrices Ri applied to alpha. So you obtain change of basis R, which is a sum of U to the di of Ri, where Ri are going to be automorphisms of E tilde. And why do I talk about these? Because they allow us to say something not just about genus 0, but about higher genus. And this is because if you have such an R matrix, then you can act on a cohomological field theory, which is by definition sort of captures all genus Gromov-Witten invariants of a space. Okay. And the main application I want to talk about here is how to obtain R matrices from the Fukaya category. So suppose that we're in some magical geometric setup, which I will give examples of in a minute, where the Fukaya category of X actually decomposes as the Fukaya category of some known spaces, Yi. Then the conjecture about the cyclic open-closed map then tells us that the quantum TEP structure also decomposes as a direct sum of the quantum TEP structures of these spaces Yi. Now, as I had said, like the quantum TEP structure comes with a natural splitting. So we have a natural splitting on the left-hand side, and we obtain a natural splitting on the right-hand side by just taking the direct sum of all the splittings we had before. And then one thing to notice is that in general, this isomorphism phi might not respect like these natural splittings. So we can pull back the splitting that we had on the right-hand side to obtain another splitting on the left-hand side. So now we have two two splittings, so we obtain an R matrix on the quantum cohomology of X. And the natural conjecture to make is that then indeed the Gromov-Witten cohomological field theory of X can be obtained from the Gromov-Witten cohomological field theory of the yi's. Or if I say it in words, this R matrix is going to recover the all genus Gromov-Witten invariance of X from the all genus Gromov-Witten invariance of the yi. And assuming the open cyclic open closed conjecture, this conjecture can be proven for genus 0 invariants. And because these are just like directly determined by the splitting. So how does that go? We have the quantum, we get an isomorphism of the quantum TEP structures, and then we just basically say like, well, they're going to be they're going to give rise to the same Frobenius manifold once we equip them with the same splittings, so that they give rise to the same enumerative invariance. And then this is just saying that if we take the Frobenius manifolds associated to the yi and we twist the Frobenius manifold by the R matrix, we obtain the Frobenius manifold associated to X. But in higher genus, why do we expect that? Is because there's this underlying geometric equivalence between the Fukaya category of X and the Fukaya category of the spaces yi. And in some way, it's conjectured that the Fukaya category not just knows about genus 0 invariants, but about all genus Gromov-Witten invariants. For example, through the construction of categorical enumerative invariants. So one way to show this would be if we could show that the categorical enumerative invariants agree with the actual honest Gromov-Witten invariance of the space X, then this conjecture can be proven. Okay, so let me give you an example of where such a geometric decomposition indeed exists. And the simplest one is for projective spaces. So if X is CPN, then morally the Fukaya category of CPN is quasi-equivalent to just the direct sum of the Fukaya categories of points. So it's really as trivial as it can be. And this tells us that we obtain an R matrix for the quantum cohomology of CPN. And indeed, it was already shown by Givental-Teleman that the R matrix you obtain in this way recovers the all genus Gromov-Witten invariance of X. But there is another important bit that Givental-Teleman show is that this R matrix is actually computable, and you can compute it just from the genus 0 3-point invariance of X. So once you have those, you can compute the R matrix and you can recover the higher genus Gromov-Witten invariance via some simple computations. And this works more generally when the quantum cohomology of X is a semisimple ring. So this is this famous Telemann reconstruction of semisimple cohomological field theories. The next example I'm going to give is an example when we can obtain an R matrix, even though the quantum cohomology is not semisimple, which I believe is the first time that an R matrix has been used in such a non-semisimple setting. And one example you could take is where X is a complete intersection of two quadric hypersurfaces in CP5. So it's a three-dimensional space. And in 2011, Ivan Smith proved that morally, the Fukaya category of X decomposes as two copies of the Fukaya category of a point and the Fukaya category of a genus 2 curve. And this genus 2 curve arises naturally from this intersection of quadric hypersurfaces. And it would follow directly from the cyclic open closed conjecture that we then obtain an isomorphism of TEP or EP structures like this. But in this case, you can also show this directly by hand. And one thing that you get from doing that computation by hand is that you find that the associated R matrix is actually going to be computable, again, just from the genus 0 3-point invariance. And I then later verify that indeed, if we use this R matrix for the intersection of quadrics, we can obtain certain genus 0 and genus 1 invariants. And like I don't know any computation that has already been done for computing genus 2 invariants for this intersection of quadric hypersurfaces. But if you have such a computation and want to share it with me so that I can verify my conjecture, then please do. I will be really interested in that. But yeah, it allows for some nice computations.
So this
okay.
direct sum, does it have anything to do with semi-orthogonal decomposition, or it's?
No, so like the Fukaya category, I would like these decompositions are always like as direct sum decompositions, even though indeed, like if you take coherent sheaves in this case on coherent sheaves on the complete intersection of quadrics, then indeed you will get a semi-orthogonal decomposition of like with two exceptional objects and the derived category of the genus 2 curve.
Okay.
Yeah, but that's just like part of this story that always like on the Fukaya category you get direct sums, and on coherent sheaves you get these semi-orthogonal decompositions. Any more questions about this before I completely switch track and talk about open Gromov-Witten invariants?
Let me quickly. So in this case, you really don't worry about the multiplication in the quantum cohomology.
No. The important structure is the E structure.
It's just the E structure. Okay.
Yeah, because you could also construct a different isomorphism, sort of that like if you quotient everything by U, you could also construct an isomorphism of just the quantum cohomology algebras. But that is going to be a different isomorphism and not the correct one.
Yeah, especially the direct sum decompositions here. I was curious about how the multiplication will be.
The multiplication will also decompose as such a direct sum.
Oh, that's interesting.
Yeah. So that is why I was saying that sort of this example is one where it's not semi-simple, because the quantum cohomology of the genus 2 curve is not semi-simple because it's just a cohomology of the genus 2 curve.
Well, thank you.
But in order to compute the R matrix, you really need to consider this E structure, and that's why I considered them. And in this magic, like in this setup, it's really nice that there exists a unique such isomorphism, so that uniquely determines for you the R matrix. And it's something that I don't understand in general, whether such decompositions are going to be unique, and that just depends on sort of what the auto-equivalences are of these E structures, and I haven't been able to figure that out in general. But there exist many other examples where you can get such decompositions, and indeed the isomorphism being unique, so you can compute an R matrix.
Also, does the decomposition respect, say, the TEP structure? Like, does it respect the pairings? Does it respect?
Yeah.
And
It
the
respects
connections
everything.
as well. Oh, yes.
Okay. Any more questions about this before I move on? Okay. So in the last 10 minutes of the talk, let me tell you about how you can use these TEP structures to talk about open Gromov-Witten invariants. And just as a short reminder, what are open Gromov-Witten invariants? These were considered by many people, but the definition I will consider today is from Solomon Tukaczynski, and we'll only talk about genus 0. And you should think of these as maps that take inputs in the cohomology of X and output some real or maybe rational numbers. And intuitively, they're just counts of disks with boundary on the Lagrangian and with some interior constraints and maybe some marked points on the boundary as well. But one issue is that if you would want to define a count of disks like this, you run into some problems, which is what can happen is that this moduli space has codimension 1 boundary. Because what can happen if these disks move around in the family is that the boundary of the disk can contract to a point, and so you obtain a sphere. And one way, like say Solomon Tukhchinsky get around this problem by doing the following. So what they do is they consider the integration map over the Lagrangian, and that's a map from the cohomology, from the differential forms on X to the real numbers. And then we consider the cone over this map. So how is this given? As a vector space, it's just given by the real numbers, direct sum differential forms on X with the differential. And then if we take the cohomology of this cone complex, we'll obtain something that they call the relative quantum cohomology after tensoring with the Novikov field. And they equip this with a TE structure. And how do they do this? I will only tell you about the T structure. So this is the connection in the Novikov direction. And how is it defined? Well, if we have a pair, so E and eta, where E is a real number and eta is a differential form, I will always sort of denote the pairs by like that. Then on the output number is just going to be given by, well, you always have to take the derivative of E. And then we add an extra contribution from this number Q minus 1, 2. And what is Q minus 1, 2? This is a way to associate the two differential forms, a number, and it's given by integrating over the moduli space of holomorphic disks with no boundary marked points and two interior marked points. And you just pull back the differential forms to the moduli space and you integrate. So this gives you a number. And on the differential form part of the element in the cone complex, you just take the usual connection that was already defined. And together, this definition is well defined on the cone complex, even though this moduli space might have one-dimensional boundary. And if you're now in a situation that the fundamental class of the Lagrangian is 0, so that this integration over L is 0 at the level of cohomology, then the short exact sequence associated to the cone complex, the long exact sequence associated to the cone will split into a short exact sequence. And in this case, it breaks up like this. So we have an extension of TE structures, which reads as follows. And now if we want to obtain an open Gromov-Witten invariance from the Fukaya category, one thing to do is to construct a similar sort of extension of TE structures, just from the categorical data of the Fukaya category. And this goes as follows. Again, you can do this in a general setup where you just have any A infinity categories, C and D. And it turns out that the natural thing you need to consider is a functor between them. And then you can consider the induced functor on cyclic chains. And then the thing I define is what's the negative cyclic homology of this functor. And it's just given by the homology of the cone of the induced map on negative cyclic chains. Okay, so that is the R join U module that we need to consider. And the point is that you can equip this with a connection. I won't give you the formula, but it's just naturally defined in terms of this functor and the differentials on here, and the connection. And the connections on here.
And you mean flat connection? Yeah. What?
That is a very good point. I say a connection here, and that's because I was unfortunately not able to show that this connection is flat. I tried to do it by writing down all the terms and showing that this is flat, and I ended up with about 36 terms, and I got lost halfway through every time I tried. But fortunately, let me get there. The situation we're going to apply this to is just the inclusion of a single object into the Fukaya category. So we take the trivial category star with like one object, and the endomorphism space is just the ground field spanned by the unit. And that has a functor to the Fukaya category by sending the unique object to the Lagrangian, and endomorphism 1 to the unit of the Lagrangian. So that's sort of the simplest functor you can consider. And then the negative cyclic homology of this functor I will denote by the relative cyclic homology of the Fukaya category relative to the Lagrangian. And in this case, fortunately, it is indeed, you can indeed check that this connection is flat, which would be really ugly if I hadn't been able to do that. And the analogy of the Lagrangian having 0 fundamental class in cohomology of X is now that the Chern character of the Lagrangian vanishes in the negative cyclic homology. And the Chern character is just defined by the class of the unit. And if that vanishes, then you obtain a short exact sequence of TE structures as follows. And if you've been paying a lot of attention, you will see that this short exact sequence goes the wrong way around compared to the one that Solomon and Tukaczynski construct. So what you really need to do is suppose that we consider now the relative quantum homology of X relative to L, which is just a dual TE structure. Then there should exist some relative cyclic open closed map, which is fits into a commutative diagram like this, so that these relative connections are respected. What I show is that if we assume this, if we assume the technical assumptions as in Solomon Tukaczynski, we indeed get such a diagram of TE structures. And again, this will only work that you don't have to you can't take the full Fukaya category, but you have to take the Floer co-chain complex of a single Lagrangian. And moreover, if you assume this conjecture has been proven in the setting in a Calabi-Yau setting, then you can actually show that this just the data of this extension of TE structures of negative cyclic homology determines, well, at least the 1-point open Gromov-Witten invariance of X relative to L. And I fear I won't have time to talk about the proof of that. So let me finish there and open questions.
Thank you very much. Are there any questions?
So I can ask a question. So this is a very kind of like an ignorant question. So what should the open Gromov-Witten invariance be? So you get this T structure. So ideally you'd like to get something like a Frobenius manifold. So you get something like a Frobenius manifold where instead of actually having a metric, you just have a connection, or what's the exact structure that you end up with?
Yeah, so this was considered in the thesis by Alcolado, and he considers these Frob manifolds.
Okay.
Which is basically a Frobenius manifold where you don't have a pairing.
Okay, so you just have a flat connection and
yeah, and instead of having like a in Frobenius manifold you have a potential, but now you have to consider something that's called a vector potential, which I guess just in some way the derivative of the potential.
I see.
But I mean, this is a very good question, because this is only the answer for genus 0, is that you want these Frob manifolds. But what should it be in higher genus? I would really like to know what it is, but sort of what sort of structure is this?
0. So is there something like, so for the closed ones, there's this procedure of from a tap with a splitting, you build a Frobenius manifold. So is there an analog here?
This is something I'm working on at the moment with Sakchu Lee, who is also at Edinburgh. But we have some ideas, but nothing concrete yet that I'm able to sort of easily explain, unfortunately. But in at least sort of in the Fano setting, you would really want to talk about sort of having this extension of TE structures, and then from that plus a splitting, obtaining a Frob manifold, and then saying that will give you that the open Gromov-Witten invariants agree. But in the Calabi-Yau setting, the approach is very different, and it's more sort of like what I'm sketching here is similar to what Ganatra, Perutz, and Sheridan do, where they just consider these variations of Hodge structures and show that in that case, the variation of Hodge structures implies for gives you the splitting for free. And in this case, that allows you as well to obtain open Gromov-Witten invariants with sort of a bit of extra data.
And in this in the geometric setting, the Solomon to Kaczynski, do they try to assemble this into one of these Frob manifolds or not really?
No. So they and this really still confuses me. Like I've talked so much with them about this, but they assemble open Gromov-Witten invariants into well, first of all, they actually define the relative connection as well, but not the relative connection in the U direction. But the main new point, what they also do is that they consider a relative quantum cohomology. So they actually put a product structure on this cone complex. But I really don't understand how to fit that in sort of into a general consideration of what open Gromov-Witten invariant should be.
Okay. Thank you.
Yeah, but maybe you two guys, experts, explain me, there is this approach which is pure categorical, yeah, like people like Caldararo and others trying to, maybe Yulina, I don't know, what's the place of that approach when you deal with topological field theory and under Hodge to drum degeneration with cohomological field theory, you can produce some invariants.
Yeah, but I don't think there's any obvious answer to what that approach should tell in this open case. So,
yeah, and there is no upgrade which kind of...
Not any obvious upgrade to include this open Gromov-Witten invariants, just the closed ones. And even that is still in progress. Like the full homological field theory is still in progress.
Okay. Mm-hmm.
Yeah, but how that relate? I mean, no, I shouldn't say this because you know all of this, but well, like at least what my understanding is that sort of these categorical Gromov-Witten invariants, they always need a splitting as well, right?
Yeah.
Yes, but it's part of the, you cannot avoid it, but you can axiomatize it. Then, of course, in the particular case you are dealing with, it's a question, as you said, what's the right splitting? This is correct, yeah. But axiomatizing the splitting, you get some invariants, and then you can state whatever the conjecture that on the right splitting you get something which geometrically gives you Gromov-Witten or something like that. So, but I haven't seen it kind of in writing. But Lina's remark is more serious that, yeah, you cannot get open Gromov-Witten invariants from that story, yeah. But, you know, I don't know, there is this notion of Calabi-Yau categories with a boundary, and with Maxim we even developed more general Calabi-Yau category with corners, and so maybe this will be an appropriate framework for this more general. Yeah, I also have another question, but it's completely perpendicular. You see, there is some categorical stuff, yeah, Fukaya categories, blah, 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 and there is enumeratives, Gromov-Witten. Okay, so then your question is how to get enumerative from categorical. Now, there is a different story, which is pure holomorphic, which people like, I don't know, Kunkov and other physicists, like in this 3D n=4 colon branches, they have moduli spaces of quasi-maps, which sort of are holomorphic, if you like, in some sense, holomorphic version of a Gromov-Witten invariants. And you can speak about also, I don't know, Fukaya categories in holomorphic setting. Has anyone thought about the relation between categorical and this quasi-map story? Analogously to, I mean, it's very different in the nature because generically there are no Gromov-Witten invariants, so you should consider them in families, these categories from the very beginning to get something non-trivial, but nevertheless, did anyone try to think about that? Because I haven't seen it, but
yeah, I only heard about this last week, so I know absolutely nothing.
Okay, not enough time, yeah. Okay, all right, thank you. More questions?
Yes, still want to digest this type structure. So with the T and E. So and T and E, is it possible to just making the T and E as just some kind of flat connection on the formal disk over R?
Yeah.
And with the
so
with
the T
the
and the E are
singularity,
together
so
flat.
the two becomes natural, or the E structure. And
I mean,
the parent is also the tensor product over the formal power series. Am I right? We go all the way back to the very early.
Yeah, so one thing is that the T structure sort of it also has some U dependence.
Yeah.
So you can't state it separately.
But the two sets, the connection actually extends to the formal disk.
Yeah. And then the total connection is also going to be flat, which is a condition that I didn't state.
Okay. So that eventually that becomes a D-module on the over the with a certain scribed the singularity of the.
Yeah.
Okay. And the parent that is also over should be invariant over the formal disk, right?
Yeah.
More questions? By the way, there is a paper in the archive exactly with the same title, so if you have kind of technical questions, you can read them or email to the author. Okay, Kai, thank you for the very interesting talk. And if there are no more questions, so this is it for today. Thank you.